Hi everyone, and welcome to our short tutorial on sampling distribution of the sample proportion. Now, you may recall that we went through sampling distribution of the sample mean. There is a sampling distribution of the sample proportion, and that is obtained by taking random samples of a given size n out of a population. So a population can have a parameter of interest, such as the proportion of young adults who drive, the proportion of students who go on from high school to university, the proportion of teenagers who smoke, the proportion of seniors who text, whatever that is. So we essentially would just generate samples from that population of a given size and observe the equivalent sample statistic. So our sample size could be n in this case, and then we just simply observe p bar 1, p bar 2, p bar 3. So if we collect all of those samples, sample proportions, 1, p bar 2, p bar 3, and we would repeat that process, p bar m, if m represents all of the possible values, then we will have a sampling distribution. What is the shape of that distribution? It's of interest to us because if it is a normal distribution, we could do some fun things with it. All right? So we have a condition to check, which is essentially np greater than or equal to 5, n 1 minus p also greater than or equal to 5. All right? So if we have that condition satisfied, then we could go ahead and we can assume that the sampling distribution is normal, and then we could do all the things that we do with a normal distribution. All right? If we are able to show that, then we have the following. The mean of the sample proportions, mu p bar, will just be the population proportion, and the standard error, sigma p bar, of the sample proportions will be given by the following formula. P into 1 minus p over n. And we take the square root of that, and that gives us the standard error. Once we have that now, given that this is a normal distribution and that's the mean and standard deviation, we could find our z values that in case we want to find probabilities. So given that that is our sampling distribution of the sample proportion, mu p bar, sigma p bar, if we are interested in a particular value of the sample statistics, say either greater than this value right here, then we will need to find the equivalent z. So the z will be given by, and if you notice, the z's have the same format, sample minus population divided by the standard error. So what's our sample? Sample minus the population, which is mu p bar, divided by the standard error, sigma p bar. But now, because we know mu p bar is p, and sigma p bar is the square root of p into 1 minus p over n, then we can rewrite this as follows. We could rewrite this as z is equal to p bar minus p, so that's population, divided by the square root of p 1 minus p over n. All right, and that's our z value right there. And we could do all the fun things with the normal distribution that we want to do. So let's work a problem. We have the following problem given to us. This comes out of our sort of a workbook, and it's problem number 38 in chapter 7, page 327, depending on which edition of the book that you use. But you can certainly find it. 42% of primary care doctors think that their patients receive too much medication. We all tend to over-medicate them. Might be a conspiracy between the medical profession and the pharmaceuticals. Who knows? We don't know. But they receive unnecessary medical care. And it all depends, like in the American system, for example, people get paid, or hospitals get paid, depending on the amount of care dispensed to a patient. So there's an incentive to sometimes to provide more care than is actually needed. Whereas in our system, because it's a single payer system, our interest is to lower cost. So we try not to do too many tests. So you need some kind of balance between these two extremes. So we are told that suppose a sample of 300 primary care doctors are taken, show the sampling distribution of the sample proportion. Okay, so essentially, just for this particular scenario, we're told 42% of the population of doctors, or primary care doctors, provide unnecessary medical care. We are taking samples of 300, so therefore, what is the sampling distribution in this case? And so let's take a look at that. So what are we given? We know our sample size taken is 300. We know our population proportion is 0.42. And so if we were to do the test, we know that 42% of 300 is greater than 5. So let's just write it out anyway. NP is equal to 300 times 0.42, which is greater than 5, and N into 1 minus P is equal to 300 times 1 minus P is 1 minus 0.42, which is 0.58, and that is also greater than 5. So our conditions are satisfied, in which case we could say that P bar is a normal distribution with a mean of P and a standard deviation of P into 1 minus P over N. All right? So that's our mean and our standard error. We could actually figure out what those values are. We already know that P is equal to 0.42. So let's find sigma P bar. Sigma P bar is the square root of 0.42. Excuse me, I'm not writing properly here. Of 0.42 times 0.58 over 300, which turns out to be 0.0285. If you use 4 decimal places. So we know what P is, and we know what P bar, sigma P bar is, and so therefore this would be 0.42, 0.0285. So that's the distribution right here. Okay. Now, part B of this question, what do we ask? In part B of this question, we ask, what is the probability that a sample proportion will be within 3% of the population proportion? Within 3%. So, essentially, the population proportion is 0.42. If we want to be within 3% of that, we must add 3% and subtract 3%. So what we are interested in is P bar being between P so P bar being between P plus or minus 0.03. We could write this out as, what's the probability? So if I subtract 0.03 from 0.42, I'll get 0.39. What's the probability of getting P bar between 0.39, and if I add 0.03, I get 0.45. So that's what I'm looking for, between 0.39 and 0.45. So if I were to draw this so you could see it as a picture, this would be 0.42, and here would be 0.45, here would be 0.39, and one of the nice things, because we know that we added and subtracted 3%, that means that those two lines are equidistant from the mean. we are interested in this area right here. All right. So to do that, we will need to find our Z values. Let's do that. So that's the same as Z being between. So I'm going to let Z1 be associated with the 0.39 and Z2 be associated with the 0.45. So let's find them, what they are. So Z2, I'll start with Z2. Z2 would be 0.45 minus 0.42 over 0.0285. Remember, we have already calculated the standard error. Now, I really don't have to put the 0.45 minus 0.42 because we're already told that we want to be within 3%. So you know that the difference between the mean and the 0.45 would be 3%. However, it's good to do it so you could actually see it in the form of a Z score. That turns out to be 1.05 to 2 decimal places. And so therefore, without any calculation, because this is equidistant from the mean, then my Z score will be negative 1.05. Cool? And so, I am interested in the probability of Z being greater than or equal to negative 1.05 and positive 1.05. In which case, I would need the probability of Z2. I mean the area associated with Z2 minus the area associated with Z1. Not too hard to see. So Z2 would give me all of the area to the left of that 45. Area associated with Z2. The area associated with Z1 will give me all the area to the left of 39. And if I subtract that area to the left of 39 from the area to the left of 45, I get what's in the middle. Just to demonstrate that, I'm going to use some different colors so you could see what I'm talking about. Let's get this out of the way for a little bit. All right, let's see what I got for colors here. So first, let's draw the graph. So this is 1.05, negative 1.05. So the green, I'm going to use to shade this area, and then red, everything. So notice that in the area to the left of 1.05, I have included the green area, this area right here. It's included. So if I want the area in between, which I will cross hatch as blue, I would have to take away that green portion from the red portion. In which case I am looking at subtracting area associated with Z2, and I'm taking away from that area associated with Z1, because this is our Z1, this is our Z2. Okay, so what is that equal to? It turns out, when we check our tables, that's 0.8531 minus 0.1469, which gives us 0.7062. So our answer is 70.62%. And there you go. That's all we have to do with this question. So the probability of being within 3% of the population proportion, 0.42. So if I want to be within 3%, I could go to the right. 3%, 0.42 plus 3% is 0.45. Subtract 3%, 0.39. The probability of being in that range is 70.62%. So now it's your turn to do C. Your turn to do C, because C now asks you, what if I'm interested in being within 5 percentage points? In other words, probability that P bar, so 5 percentage points, 0.42 plus 5 is 0.47, and 0.42 minus 5 is 0.37. Right? So in which case, that would be a bigger space because now you have 0.05 divided by 0.0285 as your Z value. So it will be much bigger. I'm going to let you solve that for yourself and repeat the entire process that I just did earlier, except that now we're working with the Z value associated with 0.05 over 0.0285. And whatever that turns out to be, negative and positive, subtract the areas like we did before, and we will be fine. All right? So that's essentially all there is to it. If we wanted to find the probability of exceeding, so instead of being within, it's really the same idea. So what if we wanted probability of being greater than, say, 0.5? Whereas we know this is 0.42. So we need this area. We'll simply go ahead and find Z. 0.5 minus 0.42 over 0.0285, in which case that'll be 0.08 over 0.0285. And I believe that's a pretty big number. If I could find my calculator. Let's see here. So 0.08 divided by 0.0285. I'm using my calculator in my computer, and it's 2.8. It's 2.8. All right. So that turns out to be a Z value of 2.8, which is fairly large. And so therefore we will have a large area in between those two. It's almost 3. So we'll be looking at 0.9 something. All right. And we could figure that out. Good. So hopefully, let's just a quick reminder. Sampling distribution of the sampling proportion comes about when you take random samples from a population and you observe the sample proportion. When you put them all together, you get a sampling distribution. If it meets the condition that the sample size times the proportion is greater than 5 and the sample size times 1 minus that proportion is also greater than 5, then we could assume what we call a normal approximation to a binomial distribution. In that case, then we would have the mean of that normal distribution to be the population proportion and the standard error to be the square root of p times 1 minus p over n. All right. Once we have that, now we have the mean and the standard deviation of that normal distribution, which is the sampling distribution of the sample proportion, and then we could go ahead and find probabilities with it, like we've done before. Okay. Thank you very much. Do a couple of problems on your own just to see that you grasp the concept, and we will take it from there. Remember that we're actually going to be using those probabilities later on in hypothesis testing, when essentially we're going to calculate the probability of observing a particular sample. And when that probability turns out to be small, so that small probability will indicate that that sample is significant, it's rare, because it shouldn't happen, and then that then causes us to question our hypothesis. So I want you to keep in mind what we learned about sampling distributions and then finding probabilities, because we will be taking advantage of that when we come to hypothesis testing, which starts in chapter 9. Okay? See you soon. Bye-bye.